Hello and welcome to the second video of the M3 chapter Elastic Strings and Springs. An exam question on the screen here to review what we did in the first video. Particle of mass 5 kilograms, that's here, 5G, is attached to one end of two light elastic strings. The other ends of the strings are attached to a hook on a beam. The particle hangs in equilibrium at a distance 120 centimeters below the hook, with both strings vertical as shown. One string has natural length 100 centimeters and modulus of elasticity 175 newtons. The other string is different. It has natural length 90 centimeters and modulus of elasticity lambda, and that's the thing we need to find. Okay, so let's set out what we know. I'll put on the left the first string in red, we know has a natural length 100 and a lambda 175. On the right, in green, the other string has natural length 90 and a lambda, the unknown we're trying to find. And notice that we also know the extension for both of these because we know that it's 120 centimeters. So on the left, this string has got an extension of 20, and on the right, this string has an extension of 30. Now we should finish our force diagram. We've got 5G, the weight of the particle there, but we've also got the tension in the two strings. Here, T1, and on the right, T2. So we can go through our usual process. We can form an equation for T1. In fact, we can find T1 because we know all of these. We can form an equation for T2 in terms of lambda with all of these, and we can resolve to connect T1 and T2 together with the weight 5G. So resolving vertically, we get T1 plus T2 minus 5G equals 0. So if I take that on the other side, that has to equal 5G. And we also know that T1 is equal to lambda x over L for all of its information, which is 175 times 20 divided by 100. And T2 is equal to lambda x over L for its information, lambda times 30 over 90. Putting these three together gives us 175 times 20 over 100 plus lambda times 30 over 90 must equal 5 times g. And then we can solve for lambda. This is 35, lambda over 3, and 5 times 9.8 is 49. So we want to get a fairly nice number for lambda of 42 newtons. In this video, we're going to use Hooke's law to solve dynamics problems. We've seen it used already to solve equilibrium problems in the previous video. Now, dynamics problems means the particle will be moving. Here's Hooke's law. We're going to be using this again, but we're also going to be using F equals ma to try and connect the forces that we know, which will include the tension, with the motion, which will probably have some information about the acceleration. And in terms of the notes, that's it. There's not much different going on here. We're just using what we already know in a slightly different way, combining things that we haven't yet combined. So jumping into the first example of 2, one end of a light elastic string of natural length 0.5 and lambda equals 20 is attached to a fixed point A. The other end of the string is attached to a particle of mass 2 kilograms. The particle is held at a point which is 1.5 meters below A. That's more than its natural length, so it's been stretched, and is released from rest. Find the initial acceleration of the particle. So this is very much an F equals ma problem. We need to find the force in order to find the acceleration, and part of the resultant force will be the tension in the string. So if I sketch this out, we've got point A up here, it is fixed here, the string is stretched down here, a distance of 1.5 meters, held at rest, and then released. Putting our forces on here, we've got the tension in the string, and we've got the weight of the particle, which is 2g. F equals ma is fairly straightforward. We've got tension minus 2g, resolving vertically, is equal to the mass 2 times a, but the problem here, and the new thing that we're doing with Hooke's law in this case, is that we don't know t yet. But obviously to find t, we just apply Hooke's law. T is equal to lambda x over L. In this case, lambda is 20, x, the extension from a natural length of 0.5 to 1.5 is just 1, and the natural length is 0.5. That gives us a tension of 40 newtons. Then we go ahead and we do this bit, which we've already done. We put 40 in here and we calculate A. So we've got 40 minus 2 times G divided by 2 is equal to A. And if I put G as 9.8 on my calculator, that gives me an answer of 10.2. And I suppose I should round that to two significant figures because we've used G as 9.8. So let's say A is equal to 10 meters per second squared to two significant figures. That is part A. Part B, the length of the string when the particle reaches its maximum speed. Okay, we need to think about this for a second. We need to consider, when does it reach its maximum speed? Now it might be easy to think it will reach its maximum speed when the string hits a natural length of 0.5. But don't forget we've got the weight of the particle to consider. At that point, when the length of the string is 0.5, the particle will be pulling it down. It will have a downwards acceleration, which means it will already be slowing down. The maximum speed is when the acceleration is 0. The acceleration is 0 when the two forces are balanced, when t is equal to 2g. And that will happen at some point where it's slightly stretched, and that's the whole point of the question. We need to know, when does that happen in terms of distance. So for part B, maximum speed is telling us A equals 0. When that happens, obviously F equals ma is m times 0, which is 0. So the resultant force, which we know is T minus 2g, must equal 0. T must equal 2g, and we know T is lambda x over L. And we know lambda and L haven't changed, because lambda and L are these two, specific to the string. X is what has changed, and that's what we need to find. So we've got 2g is equal to 20 for lambda, times x divided by 0.5. And that gives an answer of x is equal to 0.49 meters, or 49 centimeters. The length of the string then is the natural length 0.5 plus this distance here. So the length of the string, 0.5 plus 0.49 is equal to 0.99 meters, or 99 centimeters. And that is the length when it's at its maximum speed. Second and final example. A particle of mass 0.5 kilograms is attached to one end of a light elastic spring of natural length 1.5 and modulus of elasticity this. The other end of the spring is attached to a fixed point O on a rough plane, which is inclined to the horizontal at an angle alpha, where tan alpha is 3 over 4. So doing a little sine cos tan again, we can say sine of alpha is equal to 3 over 5. Cosine of alpha is equal to 4 over 5. The coefficient of friction between the particle and the plane is 0.2. We know the mass 0.5, natural length was 1.5, lambda 19.6. The particle is held at rest on the plane at a point which is 1 meter from O down a line of greatest slope of the plane. The particle is released and moves down the slope. Find its initial acceleration. Okay, so quickly sketching this out. We've got our plane, rough plane, inclined at alpha. Here we've got a fixed point O, and there's a spring here. Particle is on the end of it here. This distance initially is 1 meter. It's released and goes down the plane. Interestingly, if this were a string of natural length 1.5 released from a distance of 1, we wouldn't need Hooke's law at all, because the string would simply be slack and the particle would move under gravity only. But because it's a spring, natural length 1.5, released at 1 meter, that means it's being compressed. So there is a thrust acting this way. And when it's released, that will add to the component of the weight down the plane, increasing the acceleration as compared to it just moving under gravity. So let me put those other things on as well. We've got the weight here, which would be 0.5 g, splitting it into its components, 0.5 g sine alpha, 0.5 g cosine alpha, and of course we've got the reaction force here. I've already put the tension on, but that's not quite everything because this is a rough plane. So we've got friction. Of course friction opposes motion, so friction will be going this way. Then we do all of our usual things. We resolve to find r is equal to 0.5 g cos alpha times it by mu to get the friction. Then combine into one equation T friction and this component of the weight. That will give us the resultant force in the equation F equals ma, and from there we can find the acceleration. So that's our plan of attack. Here we go. Resolving perpendicular to the plane gives us r is equal to 0.5 g cos alpha. We know cos alpha is 4 over 5, so that gives us 2g over 5 for r, which in turn gives us a friction. Mu times r is equal to 0.2 times 2g over 5, 2g over 25. Now considering motion parallel to the plane, we've got F equals ma, because there's motion here, it's not in equilibrium in this case, and F, the resultant force, is made up of the three forces here. So putting those in, down the plane, we've got T plus 0.5 g sine alpha minus the friction must equal the mass, 0.5, times the acceleration a. On the side, let's do T. The tension is equal to lambda x over L, and that is 19.6 times the compression. Compression from 1.5 to 1 is a half, divided by the natural length, 1.5. So the tension in the spring is 98 over 15. So now we know the friction, we know the tension. I can put that into this equation and calculate A. 98 over 15. Sine of alpha we know is 3 over 5, so this term becomes 3g over 10, minus the friction, 2g over 25, is equal to a over 2. Putting g is 9.8 and putting all of that on my calculator gives a final answer of a as 6,517 over 375, so I'll convert that straight away into a decimal. That gives me 17.378 ... to two significant figures then, 17 meters per second squared. And that is the initial acceleration of this particle here. So as with the previous video, I hope a lot of this is familiar to you from previous work. We've got a force diagram here, very important, resolving. We've got F equals ma, which we've done before. The only difference here is that one of our forces is the tension in the spring, so we need to do Hooke's law for that element of the equation, put it in with all the rest to get the answer. That I hope is enough for you to have a go at the questions in exercise 2b, and maybe I'll see you for something a little bit different in the next video.